that, in fact, 3I Atlas gets near Jupiter on March 16th, 2026, at a distance which is exactly identical to the distance inside of which
I-Atlas is out here pulling off a move that no natural space rock should even be capable of, and the way it's slowing down near Jupiter looks way too clean to be random. The thing is drifting right up to the edge of Jupiter's hill sphere, that thin borderline where the planet's grip gives out to the Sun, and the position is so exact it comes off like a planned stop. No known comet has ever hit a mark like this with such precision, and now everyone's arguing about what's really guiding its motion. And if this path isn't natural, then who or what is shaping its next step? The journey of 3I Atlas through our solar system has turned into one of the wildest space mysteries in modern science. And its slow slide toward Jupiter didn't start last week. It began long before anybody noticed something weird in its movement. At first, the object showed up as a tiny glint creeping in from deep interstellar space, moving exactly how a visitor from outside our system should. Its speed looked right, its direction was normal, and even its shape didn't raise any eyebrows, so scientists assumed this was just another rare passerby that would swing through and keep it moving without doing anything shocking. But everything changed once it drifted closer to the Sun, and that subtle shift is now the center of the whole debate about whether this thing is reacting to something or actually adjusting itself. Things get even crazier when you check how 3I Atlas handled sunlight, because right after it passed perihelion, its closest point to the Sun, it showed a non-gravitational acceleration that pushed it off its original route just a bit, but in a direction that lined up almost perfectly with where it's heading today. Scientists know comets can speed up from jets of gas that burst out when they heat up, sure, but those jets are normally wild and messy. Most comets spin around, tumble, and glitch their way through space when they warm up, creating uneven thrusts that never form a clean pattern. Atlas didn't act like that at all, and that's what's making astronomers stare at it like, what is this thing? Its motion looks way too steady, like it's being guided by something inside it, or built with some structure we still can't figure out. Another wild twist in this journey is how the deviation was picked up by more than 200 observatories worldwide, all locked in on the same strange shift in motion. Every new round of data kept pointing to the exact same thing. 3I Atlas wasn't cruising on a gravity-only path anymore, and each updated model pushed its new route closer and closer to Jupiter's hill sphere, like it was lining itself up on purpose. With this much agreement across global data, it's hard for anyone to shrug off the change, especially because that tiny acceleration nudged Atlas by the perfect amount to land it right on its current target. Maybe it could still be natural, sure, but the timing, the angle, and the level of precision keep pulling scientists deeper into the mystery of what's really going on out there. What makes everything even more surprising is how calm Atlas stayed while moving inward. Most interstellar objects break apart, crack, or spin out when the Sun starts cooking them, but Atlas didn't show any major signs of falling apart. It actually looked more stable and floated forward with this smooth, steady motion that nobody expected. That chill behavior made researchers think the object might have some unusual structure or chemistry that helps it stay solid under heavy radiation. And once you stack all these clues together, it becomes clear that this maneuver near Jupiter isn't some random moment. It's the latest step in a long chain of tiny, precise moves that started months earlier when it slid past the Sun. This whole pattern sparks a serious question about what kind of force can guide a path this clean for so long. If the motion came from random outgassing, then why did it form such a perfect push toward one exact location in space? And if it wasn't random, then what kind of mechanism could control the path of an object drifting in from another star system? These questions push us straight into the next part of the story, because the answer might be hiding in the extreme precision shaping its current approach. The level of accuracy in 3I Atlas's path right now is the most shocking part of the whole event, and the numbers behind that alignment show just how unusual this situation really is. 3. I-Atlas is set to swing past Jupiter at roughly 33.24 million miles, but the newest measurements show something way crazier. It's sliding in only about 35,000 miles from the exact point where Jupiter's pull balances with the Sun's. That's an error of 1 part in 26,000, a level of accuracy you barely see even in engineered space missions flying with computers and guidance systems. To really feel how wild this is, picture throwing a needle from Los Angeles and having it land perfectly on the edge of a coin sitting in New York. Natural objects don't pull off shots like that, especially not after drifting across billions of miles of space with nothing steering them. And it gets even more serious when you compare this to how interstellar objects normally act, because they roll in with messy spins, uneven surfaces, and unpredictable reactions to sunlight that can shove them in all kinds of directions. Even tiny heating changes can kick them off course, so astronomers usually expect their final trajectories to spread out into a wide range of possibilities. But Atlas broke all those expectations, and every new update is tightening the path instead of widening it, like it's locking itself onto a line with purpose. This tightening accuracy isn't just some cool scientific detail. It hints that the object is following a clean, stable path that doesn't match the noisy, chaotic patterns of natural comets. The data also shows that this precise approach didn't build up slowly over time. It kicked off right after Atlas swung past the Sun and got that tiny, strange boost, just enough to shift its path in the exact way needed for it to slide right into the narrow zone around Jupiter's Hill sphere. If that nudge had been even slightly stronger or weaker, the object would have missed the boundary by millions of miles. The chance of a natural push hitting the perfect strength and direction like that is extremely low. And that's why more researchers are starting to question whether simple physics can explain this move. The whole effect feels less like a random burst of gas and more like a final steering adjustment, the kind spacecraft use when they're lining up for a maneuver. And the alignment matters, because Jupiter's Hill sphere isn't some spot comets usually tiptoe toward. When they drift near Jupiter, they get yanked in or tossed out fast and almost never stop near the outer edge the way Atlas is doing right now. The fact that Atlas isn't getting pulled into Jupiter's stronger gravity, but instead gliding right along the edge of the boundary, makes the whole move look even more intentional. It's drifting beside that line like it knows exactly where the forces balance out, a kind of controlled approach you'd expect from a planned mission, not from some random piece of space rock floating through the void. When you line up the tiny error margin, the sharp correction it made near the Sun, and the strange choice of target, it becomes pretty clear this is not a normal, sloppy comet path. Something is keeping this object locked onto a route that follows one precise mathematical line across millions of miles, and if that's just coincidence, then it would be one of the rarest ever caught in astronomy. But if it isn't coincidence, then things get even more intense. Because what kind of process can guide something from another star system with timing and accuracy this perfect? Jupiter's Hill sphere isn't just some random zone either. It's one of the most important gravitational structures in the entire solar system. Understanding how it works shows exactly why Atlas's behavior is so strange. The Hill sphere marks the point where a planet's gravity overtakes the Sun's pull, and for Jupiter, that zone stretches tens of millions of miles across like an invisible bubble of influence. Most natural objects never end up on this boundary because their motion gets tossed around by chaotic stuff, solar radiation, collisions, uneven heating, all that. They either tumble deeper into Jupiter's gravity well or stay outside where the Sun keeps control, which is why the boundary acts more like a mathematical idea than a place anything actually aims for. So the fact that Atlas is sliding toward that razor-thin transition zone with such precision is already wild enough on its own. What makes it even stranger is how the forces flip depending on which side you're on. Inside the Hill sphere, Jupiter becomes the boss. It can grab you, speed you up, or drag you deeper in. Outside of it, the Sun takes over and things move more steady and predictable. That's why seeing Atlas hover right near this invisible line, instead of falling in or drifting away, has everyone wondering what kind of control is really behind its motion. The edge between these two zones is a super fragile border where even the tiniest shift in speed or angle can send an object into two totally different futures. Because of that, it's extremely rare for a comet to hit the exact distance where the Sun's pull and Jupiter's pull balance each other out. That boundary isn't a spot where natural objects slow down, stop, or carefully change direction like they're following a plan. It's usually crossed fast and without control. The comparison gets even sharper when you look at how real space agencies use gravity. When engineers design spacecraft routes, they depend on huge gravity wells, especially Jupiter's, to pull off slingshot maneuvers with insane accuracy. These moves take tight planning and perfect timing because even a small slip can kick a spacecraft into a completely different orbit later on. Missing the Hill sphere's edge by just a few thousand miles can shift a mission's path by millions of miles down the line. And if it's that tough for human tech to hit this boundary dead on, seeing an interstellar object behaving with that same level of precision makes the whole situation way more suspicious. Another thing that jumps out is how thin this transition zone really is. The Hill sphere itself is massive, but the exact line where gravity switches from Jupiter to the Sun is razor-tight compared to the space around it. Hitting that line is like trying to land on the edge of a shadow that's moving, because its position changes a little with every orbit. That's why Atlas lining up with it so perfectly doesn't make sense as random chance. The more scientists dig into it, the more obvious it becomes that this approach is way too steady and way too clean for a natural traveler that's been drifting through unknown space for millions of years. All of this leads to one tough question. If the Hill sphere isn't a place natural objects aim for, then why is Atlas parking itself so perfectly on that invisible line? This whole thing starts to feel like a precise parking maneuver once you look at how 3i Atlas shifted its direction after passing the Sun. That small adjustment looks almost exactly like the kind of controlled correction spacecraft make when locking onto a target. The object got a gentle push that nudged it away from its earlier track, and the strength of that push was nearly perfect for guiding it right toward Jupiter's Hill sphere edge. Sure, natural comets do get tiny forces from gas jets when they heat up, but those jets spray in random, uneven ways that usually shove objects into messy, unpredictable motion, not into a perfect, laser-straight line the way Atlas is moving now. Atlas hasn't shown any of that wild, chaotic behavior you'd expect from a normal comet, and instead, it keeps gliding along this steady line that somehow matches every fresh prediction with scary accuracy. One reason the whole shift feels intentional is the timing, because that correction kicked in at the perfect moment. If the change had happened earlier or later in the trip, Atlas would have never lined up with the razor-thin boundary it's sliding toward right now. Timing matters like crazy out here because the solar system is packed with moving planets, shifting sunlight, and random forces that can knock an object off course fast. Most comets fire off messy bursts of gas that act like tiny explosions, and those blasts usually cancel each other out instead of pushing an object in one clean direction. If Atlas acted like a typical comet, its path would have drifted millions of miles away from the region it's heading into today. But instead, that soft push it got formed a clean, smooth correction that set it on a route aimed at one exact mathematical point in space. And the motion gets even more interesting when you stack it up against the way humans navigate spacecraft. When a mission needs to hit a delicate target in space, the spacecraft usually makes a late course correction after sliding past a massive object like the Sun. That little nudge fine-tunes the route without wasting energy. Atlas fits that playbook perfectly. It made its adjustment after passing perihelion, then locked onto the corrected line with almost no drift at all. Watching it hold that route, gives off the vibe of something reacting to gravity in a controlled, smart way, and that's why some scientists are saying it's moving more like a probe than a casual chunk of space rock. Its choice of destination only adds more weight, because the outer edge of Jupiter's Hill sphere is a spot where tiny forces can flip everything. It's a zone where Jupiter and the Sun are basically arm wrestling, and that makes it a sensitive place where an object can slow down or switch behavior. A natural comet would usually get yanked inward or shoved outward long before it ever reached this line. But Atlas is cruising along that boundary with a stability that shocks everyone. That kind of stability hints that the object might have physical properties that keep it balanced in ways most comets could never pull off. And when you put all these pieces together, the shift near the Sun, the locked-in route, and the strange target, the whole picture gets way more mysterious, because everything lines up with what you'd expect from a clean, deliberate adjustment. If this was just some lucky accident, the odds of all these elements lining up so perfectly would be unbelievably tiny. But if it wasn't accidental, then we've got to face the real question. What kind of internal process could pull off a maneuver that looks this much like a planned move? The question of what's actually guiding 3I Atlas gets even more complicated once you look at the four main explanations scientists are throwing around, because each one is trying to explain something that barely has any precedent in modern astronomy. The most cautious idea is that maybe the path we're seeing today comes from simple observational mistakes. Early measurements on fast-moving objects can be tricky after all. But more than 230 observatories have now tracked Atlas, and every new dataset keeps confirming the same route with tighter and tighter certainty. With this much agreement worldwide, the error theory is getting harder to defend, especially since the object keeps matching predictions with surprising precision. The second idea is that Atlas might be getting pushed by outgassing in some rare but technically natural way. Heating can trigger repeating gas jets that nudge a comet gently in one direction, especially if the jets come from cracks or weak spots lined up just right. Under perfect conditions, those bursts could create a steady-looking push instead of a chaotic one. But here's the issue. Those jets would need to fire with exact strength and angle for a long stretch of time, and even a tiny change would send Atlas drifting millions of miles off its current target. The amount of coincidence needed makes this scenario possible, but extremely unlikely. A third explanation is straight-up coincidence, because the solar system has been around for billions of years, and plenty of interstellar objects likely cruised through without anyone noticing. If even a few passed near Jupiter's Hill sphere over the ages, then Atlas could just be another rare example of something natural that just happens to be lined up right now. Not impossible, but the crazy precision of the alignment and the clean path leading here make coincidence a weaker answer than most scientists are comfortable with. Then there's the fourth explanation, the one sparking the biggest debates, because it suggests Atlas might be reacting to forces in a controlled or semi-controlled way. And this idea doesn't even require the object to be artificial. A weird internal structure or unusual chemistry could let it use sunlight, gravity, or slow internal processes to guide itself without any technology at all. Some researchers even suggest that if an advanced civilization exists out there, they might navigate through planetary systems by riding gravitational wells and boundary zones, like Jupiter's Hill sphere. No matter which explanation you lean toward, Atlas is acting in a way that's pushing every theory to the limit. Even though there's no direct proof backing that theory, the way Atlas keeps moving has left the door wide open. These four explanations outline the possibilities, but none of them shut the mystery down. And if the answer isn't error, coincidence, or normal outgassing, then what kind of process is steady enough to guide a journey this precise? Jupiter has always been a major player in the solar system, and understanding why 3I Atlas is drifting toward that giant helps explain why some scientists think this path might involve more than basic physics. Jupiter is the heavyweight of the planets, And its gravity is so powerful that space agencies use it like a natural engine to redirect spacecraft while barely touching their fuel tanks. One clean pass near Jupiter can speed a mission up, slow it down, or flip it onto a totally different direction. It's basically a cosmic navigation gate. Its gravity well shapes anything that comes into range, whether it wants to or not. And the outer edge of Jupiter's Hill sphere? That spot is even more important, because it's where Jupiter's pull balances perfectly with the Sun's. That balance point creates ultra-sensitive regions where small changes in speed can send an object into a whole new path. These spots act like stepping stones that spacecraft can sit in with almost no effort. But getting there takes careful timing and super accurate maneuvering, even with modern tech and decades of engineering know-how. So when you compare all that with Atlas's smooth, locked-in approach, it's hard not to notice how similar the pattern looks. And Jupiter matters for another reason. Gravity wells like this one can help any object, natural or not, move through a planetary system while using almost no energy. If something wanted to conserve power, gather data, or shift between different routes, this boundary would be the perfect place to hit. Even natural objects can get tossed around hard when they enter a zone like this. But Atlas is gliding toward it with this calm, controlled vibe that's making scientists stare at the data like, how is this thing staying so steady? That smooth motion raises real questions about whether the object might be using this gravitational terrain in a way we haven't figured out yet. The fact that Atlas seems to be slowing down as it approaches this region makes the moment even stranger, because a slowdown near the Hill sphere could mean the object is getting ready for another shift. It might change direction, pause for a moment, or interact with the gravitational field in some way that kicks off a whole new type of motion. These possibilities make Jupiter a major key in this whole mystery, since it's the one place where tiny forces can flip an entire trajectory. And if Jupiter really works like a gateway for movement inside the solar system, then the big question becomes, what is Atlas planning to do once it reaches the edge of this huge gravitational frontier? The approach of 3I Atlas toward Jupiter has sparked three major scientific scenarios that experts think could unfold in the next few weeks, and each one has the power to flip our understanding of interstellar objects. The first possibility is that the object might break apart once it reaches the edge of the Hill sphere. The tug-of-war between Jupiter and the Sun can create intense tidal stress, and a lot of comets crack under that pressure. If Atlas breaks, it could expose its inner structure in a way no telescope has ever seen. Layers, cavities, strange materials, all of it. A breakup would give scientists a rare chance to examine pieces from another star system up close, something that barely ever happens. But it would also raise the question of how this thing managed to survive the journey up to now without falling apart. The second scenario is even more mysterious because some researchers think Atlas could start releasing smaller bodies or particles as it slows near the boundary. Natural objects do shed fragments sometimes, but doing it right at a gravitational transition zone could hint at something way more organized. If Atlas drops pieces that slide into stable orbits or drift in clean, recognizable patterns, astronomers would start analyzing their shapes and movements to see whether they behave like normal comet debris or something new entirely. Any pattern that looks too neat or too coordinated would flip everything we thought we understood about what an interstellar object can do. Even the idea of a payload release sounds wild. But if a small cluster of fragments drifted together in a clean formation, it would spark serious conversations about what the object is really doing out here. The third scenario is the one that shocks people the most, because Atlas might switch direction again once it reaches the outer edge of Jupiter's territory. A shift like that would show the object is reacting to the gravitational terrain in ways that don't match the behavior of a simple comet. If it turns onto a new track, slows down even more, or slips into a temporary orbit around Jupiter, scientists would finally have evidence that its motion involves more than random cosmic bumps. A sudden move would also give experts a fresh chance to tighten their models and compare Atlas's behavior to what we see during controlled maneuvers from spacecraft. Even a tiny adjustment could end up being one of the biggest clues in this whole investigation. These three possibilities show just how unusual this moment really is, because each one points to different secrets about Atlas and the forces shaping its journey. If the object breaks apart, drops fragments, or shifts into a new direction, every outcome would change the questions scientists ask about how interstellar travelers move. And if even one of these scenarios comes true, what will it tell us about the real nature of this visitor heading toward Jupiter? The path of 3I Atlas is starting to feel less like a random flyby and more like a chain of decisions playing out step by step. Its perfect stop at Jupiter's boundary gives off a vibe of purpose that natural objects almost never show. The alignment, the timing, and the steady approach all point toward a moment that could reveal something way deeper than a simple comet drifting through space. Whatever happens next could reshape how we look at visitors arriving from beyond our solar system. And if this stop really was intentional, then what is Atlas getting ready to do when it starts moving again? Share your thoughts below, and remember to like, share, and subscribe to StellarDrift channel for more investigations.